It's my great pleasure to introduce our recent efforts on introducing machine learning techniques into data collection and analysis at LCRS. So yeah, let's first convince ourselves of the need of the machine learning in data collection and analysis. In LCRS, there's a special XPC mode called the split and delay mode. People call it X-ray photon fluctuation spectroscopy. It's basically the X-file version of XPCS. So it gives you the ability to measure ultra-fast dynamic process of time scales from picoseconds to tens of nanoseconds. It's very popular technique that it's not unusual that people usually wait for months until they get the chance to measure for several shifts of beam time. And you sort of cannot expect too many data points get measured per shift in order to get reasonable signal to noise ratio. So basically, it's a very limited beam time resource, let alone the first shift is almost always used for preparing tasks like alignment. Meanwhile, ultra-fast dynamics can be complicated. For instance, you might have multiple quasi-particle excitation modes that gives you the more complicated time-dependent profile than stretched exponential functions. So given the limited beam time and complicated dynamics we want to measure, one important question to think is how can we make more informed decision or plan during the data collection? And another challenge comes from the dramatically increased data repetition rates. So basically, you can expect a 10 to the 6 XPCS image per second in the future, and the resulting data throughput is sort of astonishing. But we know that not every data is useful. So in this case, another important question to think is how can we sort of analyze data on the fly in order to dig out the most valuable data from tons of collected data per second. So in today's talk, I will introduce our efforts on answering those two important questions with two specific topics. The first topic is on augmenting traditional Bayesian experimental design with machine learning, demonstrated by measuring some magnon excitation with XPFS. And in the second topic, we will see how neural networks enable on-the-fly data analysis for single particle imaging. Let's get started from the first one. So here we consider XPFS measurement, where you have some interesting magnetic materials, and you want to basically map out the intermediate scattering function by tuning the delay time t between two X-ray pulses. Let's say the magnetic structure can be described by some Hamiltonian with some parameters of interest. For example, the symmetric exchange J and the anti-symmetric exchange D. In elastic scattering measurement, the magnitude of this D here, like we have the non-zero components in the z-axis, third axis. The magnitude of this D can be informed by the gap opening at this K point for this particular van der Waals magnetic system. Correspondingly, in XPFS, if we align the sample and the detector to measure this K point, we can essentially extract the squared intermediate scattering function, which we denote as this small s, from the intensity correlation function, G2 function. So basically, this is the G2 function -1 divided by the contrast. And of course, we might have some undesired intensities, like elastic scatterings, besides our magnon-rated intensities. So let's first So this is basically the system, physical system that we set our numerical experiment on. And let's first get a sense of how traditional Bayesian experimental design works, which is quite well established. Suppose at some point of the measurement, we have an estimated distribution of material parameters x. Here, in our case, x is a vector of parameters j and d. And if we have this distribution, we can basically draw samples from this distribution. And for each sampled parameters, each sampled set of parameters, we can compute the measurement signals. And from the computed measurement signals, we can further calculate this so-called utility function. So this utility function is some function whose maximizer gives us the suggested measurement for next iteration. And I will introduce this in more details in next few slides. So then once we get the suggested measurement from the utility function, we can tune the facility and get the wait for an hour, maybe get the measurement for the for this delay time point. And then after you getting the measurement, you can sort of estimate the likelihood of each point of your parameters. And this likelihood can then be multiplied with the prior based on the Bayes theorem to get to the posterior. So this is basically a posterior. And then you kind of get the updated distribution of your parameters after each time you get a new measurement. Sorry. Yeah, so however, there exist two potential problems that makes this strategy not suitable for every experiment. The first problem is in this step, in the sampling step, basically each sampled set of parameters requires a forward model computation. So in order to get the accurate calculation of this utility function, it requires considerable number of model evaluations. And the second potential issue is this whole Bayes update loop is strongly dependent on the initial prior or the expert's opinion on the possible values of your parameters. So if you provide some not so good initial prior, then this could fail. This loop could fail. So in order to handle the first challenge, here we train a machine learning surrogate model to achieve affordable and scalable for the computations. The basic idea is very straightforward. We train a fully connected neural network to predict the Magnum modes from the parameters, and then calculate the XPFS signals from predicted Magnum modes by basically doing Fourier transform, convolve with post duration, and considering the Magnum scattering. Yeah, so there's nothing too fancy going on here, and the MLP model can be trained fairly easily. Here's the testing data comparison. The horizontal is the true value, and the vertical is the predicted frequencies and the dynamical structure factors. And we can see pretty good, excellent agreement with the testing data. So here, since the ground truth is prepared from linear spin wave theory, you can think this is basically a very fast calculator for the linear spin wave theory. But if you have if your modeling requires more advanced calculations, you can also train the model to your specific calculations like DMRG or ED. So now that we have the ability to do very fast for the computation, how can we make decision based on this? Basically, here's a brief summary of the so-called utility function, which we can define the utility function. So the main target, the main goal is sort of we want to have maximize the information gain per upon every new measurement. So we can express this mathematically by make the distance between two distributions maximized. So basically, the two distributions are the distributions before and after taking the new measurement. And this expression can be sort of reduced to the difference between two differential entropies of two distributions. And if everything is sort of nicely Gaussian, then the first term becomes the expectation of log variance of the noise. So this is only measurement noise related. In the second term, so the second term is basically the another variance, but this variance comes from the both measurement noise and the distribution of simulated experimental signal. So basically, if it's Gaussian distribution, this is Gaussian, you can decompose this total variance into the sum of the variance of noise and the variance of the simulated S of t. So basically, this term here reflects the uncertainties in your parameter estimations. So you can see here the main message is basically we have the utility function based on the noise and the parameter uncertainties. And in practice, in order to keep everything fast and simple, we only take this variance of S of t as our final used utility function. So for those who are interested, here is some related references, and this optimized Bayes experiment is a package developed by these two authors that we are using in this work. And here's an illustrative example for how this Bayesian experimental design works. So starting from, let's say, from some point where we have already made n measurements, and we have some estimation of the distribution Pn of x. And so basically at this moment, we have our mean model prediction as shown by this blue curve. So basically, based on this distribution of parameters, we can then calculate the utility function. So what we do is we draw parameters from this distribution, and for each sampled parameter, we calculate the S of t, and then we calculate the variance of S of t at each point, at each time point, and the utility function is sort of illustrated by the shaded area here. And we find the maximizer of this utility function, which is around this 1 picosecond. And basically, this is the next point we are going to measure. And once we take this measurement, we can compare this value with every calculated value from these individual set of parameters. So, and basically calculate the likelihood. So the idea is any parameter that gives close S of t to the experimental measurements will have higher values in terms of the likelihood. Once we get the likelihood and we have the prior, we can apply the Bayes theorem to get the posterior. So this is a updated estimation of the parameters, and this will be used as a prior for the next iteration. And this whole process can be better visualized by this animation. So basically, we start from 0 measurements and have a very broad prior. Then after we taking more and more data, we get more and more accurate estimation of the parameters. And this is a prior, likelihood, and the posterior. So basically, you can see how the model prediction is getting refined after taking more measurement. And since we use the neural network surrogate model, we can essentially calculate the utility function within seconds. So this basically allows us to make experimental decision based on linear spin wave theory and Bayes theorem. Sounds like a reliable plan to me. And if you have ED data, let's say, you can train another model. So in that case, you will base your experimental decision on ED result or DMRG result, whatever computation method you would prefer. So although we kind of solved the first challenge by using a network model, then but still the Bayes update is vulnerable to bad initial prior distribution. And here, we actually can address this issue by adopting those optimization enabled by automatic differentiation. So let's first see how this bad initialization can affect the this Bayesian design. So let's say we are looking at the example where the true value of j is below -2.5, but we are sort of starting with a prior that excludes the true value. And we will find that after 20-ish measurements, our parameter estimation is still very far from the ground truth. And if we look at the estimated parameters, we will find the majority of them kind of get stuck at this wrong region. So you might think right now we already have like more than 20 delay time points get measured. So can we make full use of those already obtained measurements? So actually, the answer is yes. We have this already 20-ish measurements made, and this is our current model estimation based on this wrong parameter distribution, basically. And we can quantitatively describe the discrepancy by some loss function. Remember that our forward model is basically a neural network plus some math operation. And this means this from here to here is differentiable. So we have the gradient of loss with respect to our parameters instantly available from automatic differentiation. Then we can use any kind of gradient descent based optimization to update these clusters of parameters. And if we just kind of go ahead and apply the gradient descent, we will find the distribution now has more weights near the true value, but still it's sort of far away from the ground truth, but it's already enough for the Bayes updates to correct itself and get close to the true values in next few iterations. And in practice, we apply this gradient descent correction every 14 measurement iterations. So that is only one example I have shown. So in order to sort of more comprehensive understand the performance, we can test the different strategies on the different combinations of parameters J and D. So here is basically the benchmark result over 100 different sets of parameters J and D. The horizontal axis is the measurement iteration. So here's 0 measurements, and here you have 40 measured delay time. The vertical axis is the absolute value of differences between the estimated J and the true J. So basically, you can see the Bayes plus GD. GD represents the gradient descent, gives you the lowest online estimation error. And here I'm just plotting the error distribution for the last measurement iteration, and you can see the Bayes plus GD gives you very concentrated distribution of errors around this very low error region. And this particular case is benchmarked on sort of particular noise level, artificial noise level, and post duration. We can further benchmark this, repeat this benchmark for different noise levels and pulse durations. And this is a result collected from 6 different experiment scenarios. And we can find that the Bayes plot GD consistently outperforming other strategies. And similarly, this combined strategy will give you better estimation for another parameter D as well. Apart from better online estimation, we can also expect more valuable information from measurements suggested by the Bayes plus GD. Here we consider the absolute value of derivative ds over dt as an indicator of how usefulness each suggested delay time is in capturing the peak and the valleys. Since the regions near the extreme typically have higher values in terms of the absolute value of ds over dt, then if one strategy gives you higher average of this value, then it means the suggested measurements appear more frequently near the valley and the peaks, basically. And here's the benchmark results, again, over 6 different experiment scenarios and 100 different sets of J and Ds. We find that this Bayes-based strategy gives around 20% higher, 25% higher absolute ds over dt. Yeah, it's also interesting to look at the distribution of suggested measurement for the 100 testing samples. We have x-axis for each of these surrogate plot. We have x-axis representing the measured iteration, and the number of time. The y-axis represent the measured time domain, basically. So at each vertical slice, you have the suggested delay time for 100 different J and Ds. So basically, we find that for those 2 Bayes update strategies, the algorithm sort of know where to measure in the beginning. Like if it measure this region for any kind of JD, likely to get most of the information out. Then the choice kind of split, but then sort of fill out the whole measurable domain. So basically, it says it's kind of I don't want to measure this region at this moment, but I sort of need to measure this again to get better estimations. So. But on the other hand, if you look at the sequential and the random strategies, the sequential only gives you the trivial linear pattern, and the random strategy sort of cover the whole measurable domain uniformly. Yeah, but I guess you don't really get too much information by staring at those plots. Just want to show some interesting perspective. That's all I want to share for the first topic. There are certainly lots of directions to explore. For example, we can consider more advanced network modeling, for example, including the momentum space. Here's the recent work from Josh's group, where we try to use implicit neuron representation to fit inelastic neutron scattering data. You can imagine this can be adapted to our current framework. Meanwhile, if you don't have a model, you can also adopt some Gaussian process, which is sort of model-free, and you can also train neural network kernels for those Gaussian process. And we can maybe consider utility function learning instead of doing lots of simplification and reduction. We ending up with the variance function. We can maybe just use the network to replace it. Train a neural network to replace it. And we have applied some in-house bin time, and hopefully we can get a chance to apply it to real experiments. And of course, please let me know if there's anything interesting in your mind, and maybe we can work on something together. Yeah, let's now look at the second topic, how machine learning enables data analysis on the fly. For the single particle imaging. Yeah, here's just very brief introduction to the single particle imaging. It's basically an imaging technique that gives you the diffraction pattern from single macromolecule. So you basically have some particle stream goes on that feed you particles, and you have this repeated X-ray process to take images from each kind of incoming particles. So at the end of the day, we basically obtain a bunch of diffraction images with unknown phases and unknown particle orientations, because they can kind of be shot by X-rays in any orientations. Then the diffraction patterns are, we know the diffraction patterns here are essentially the slices of the 3D reciprocal space volume, basically the intensities or the squared Fourier transform of the electron density. And once you get the 3D intensity map, you can do the phase retrieval to get your 3D electron density. And in practice, this algorithm can be only more complicated by looking at this diagram. So basically, let's say we start from some random row of R, and we can take slices, generate slices based on the random model. Then the generated, the slices just means the diffraction pattern in this case. So we can compare the generated slices with experimental diffraction patterns. And basically, by doing that, we are estimating the orientations for the experimental images. And once we estimate their orientations, we can assemble them together to the 3D intensity map, and then we feed them to the phase retrieval loops. So this is called the MTIP algorithm. And so because this, you can imagine that there are lots of complicated and expensive calculation going on if you want to do this, get your electron density in this way. But in real experiments, we might not have we don't have enough data, like it requires thousands of images to get a reasonable 3D reconstruction. So is it able to use neural network to get some density from individual diffraction patterns? So to be more specific, we are interested in training a model that can perform this end-to-end reconstruction, even if users only have one diffraction image taken and with any orientation, like unknown orientation. So is it even possible? Well, it's like the work of the PIFU model, where they reconstruct the whole 3D model from single view of image. So basically what we are doing here is similar, but it's just that we are starting from a single image in a reciprocal space, and then we want to have a 3D volume in the real space. Okay, now let's start to build a network that can hopefully do this job. There are two key features that we want to have in this model. The first one is equivariance. Basically, this means if we have equivariance and if we have the in-plane rotated diffraction patterns, we will still get stabilized, very stable encodings. So this is sort of the package we are using, called ESCNN. And you can see the features generated by this equivariant neural network is much more stable than the features extracted by this conventional convolutional neural network. And the second feature we want to have is the sort of the ability to recognize which diffraction patterns belong to the same particle or the same set of electron densities. There is a technique called contrastive learning. Basically, what it does is tries to bring the embeddings of the same level close together. So you can think these labels in our case is just different, like two different particles. Once we have a very nice encoder, then the decoder is just something like a ResNet decoder to bring the latent code to the 3D electron densities. And here's a more intuitive view of what each component in encoder does. So let's imagine we have a particle, 3D particle like a protein protein's electron density sitting at the center of this sphere. And we can basically shoot X-rays from any angle towards the center of the sphere. So we are basically shooting X-rays from different angles to take different orientations, diffraction patterns. And if we fix the polar angle and rotate the azimuthal angle, like the ring of these red circles, we will essentially get in-plane rotations, like a series of diffraction patterns that are in-plane rotations of each other. And if we tune the polar angle, then we obtain quite different diffraction patterns, as you can see here by column. So then it is quite clear that the equivariance takes care of this dimension. So basically, if you have in-plane rotations, the equivariance will give you similar latent code. And the contrastive learning will take care of this direction, basically. So it will try to bring those different images close together in the latent space. So yeah, everything looks great, and we then train a network on the simulated data. Here's the testing error sorted by their value from lowest to the highest, and it's just here is just the histogram or the density of loss. And we then select a few representative examples at each level of testing loss and plot their first 5 testing images. You can see it's not very easy to tell that those diffraction images comes from the same electron density by naked eyes. However, if we look at their corresponding latent codes, we will surprisingly find that they are clustered together nicely. So each color represents a distinct, like a unique protein here. Yeah, so if we just feed the corresponding latent code from those images to the decoder, then we can obtain the reconstructed 3D volume. So basically, the first row is constructed from the first row of testing images here, etc. And so basically in our testing dataset, we prepared 400 testing images for each protein. That's why you see lots of latent codes here, more than 5. So we can do the reconstruction for all 400 of them and average their prediction, average their reconstruction. And here's just like the 3D volume average from 400 testing images. And the top row is the ground truth. So from left to right, we have the lowest testing error to the highest testing error. So you can tell that some of the examples start to losing fine details in the sort of worst region. But in general, they are doing a good job keeping the main feed profile of the 3D volume. Let's look at more closely into the latent space, like how they are arranged by the polar angle. Here's the example where each color represents a different polar angle, and the same thing in the latent space. Interestingly, for each angle, so you can see this is basically the 0 polar angle. This is some, yeah, I don't remember the exact number, but you can see it's kind of going this way. And then interestingly, for each angle, the quality of reconstruction varies. So in particular, in this particular case, the hollow cylinder with fingers, basically, if you look at from the top of the particle, you will get the worst reconstruction. But if you kind of increase the polar angle, then you get more information from diffraction patterns. I think this is more informative. So basically, if you take images from here, then you will get better reconstructions. So I think it's basically the network finds it easier to find to learn the connections from these images to here than from this image to here. Yeah, so lastly, it's also interesting to note the connection between the reconstruction error and the Hall spread of the latent code. So here I'm plotting the scatter plots. The horizontal axis is the mean squared error of your reconstruction in real space, and the vertical axis is the standard deviation of your latent code. We can see in general there are some positive relationship between these two metrics, mainly in validation and testing dataset. But there's no clear connection in the training set, which we suspect it's because of overfitting, but we are not entirely sure now. Yeah, anyway, we think this could be an indicator, useful indicator for things like, do I need to keep collecting more data? So the basic idea, basically the idea is if you see your standard deviation, if you you are collecting diffraction images and you feed them into your encoder, and if you see the standard deviation of your latent code getting stabilized, it's not changing, which means your current data set is covering basically enough orientations for you to perform the reconstruction. And you should be good to stop collecting more diffraction images. And also another useful indicator is sort of if you observe small standard deviation in your latent code, then it means you are likely to get a good reconstruction from your network. And you can use that as the initial volume for the MTIP algorithm for better resolutions. Yeah, so of course there are lots of interesting things to do further. Maybe you can predict orientation from the encoder as well. Sometimes multi-panel detector are used, so we don't have these complete images. We have some kind of missing pixels or missing information in the middle. So how about predicting from those broken images? The detector can also take other architectures like implicit neural representation for stronger expression capability. Right now we are penalizing different labels, no matter how their real space volume are close or not. So this could also be improved, and maybe just train different models for different types of proteins. Here we only consider a very limited range of molecular weights. And very importantly, how can we incorporate this into the current pipeline? Yeah, just to summarize what we have seen, the first is the machine learning enhanced Bayesian design method, and the second is the sort of network that generates that reconstructs 3D electron density from individual diffraction patterns. And I would like to acknowledge and thank my advisors, Josh and Chuck, for their advice and support. And with that, I'd like to thank you again, and happy to take any questions.